right, I think we need to start. The first talk of this morning talk, speaker is the Chiung from China. Come here.
USDC. Yes, thank you. Yeah, thank you for the introduction. So first of all, I'd like to thank all the organizers for putting this wonderful meeting together here in Trieste. And I'm very happy to have this opportunity to talk about this, our ongoing work, algorithmic dualization of unitary circular quivers, which should appear soon. And this talk is also based on a series of works with wonderful collaborators, Riccardo, Simone, Fabio, Sara, and Matteo. Most of them are here as well. Okay, so let me first show you this picture. So this is what I draw using ChatGPT. So as you can see, this is a story about a story written by Mark Twain, The Prince and the Pauper. So it is a story about two boys, which who have very similar lookings, but completely different lives. Okay, so one is prince and the other is pauper. And the thing is that, so the thing is that even though their appearance is very similar, they live completely different life. And I found a similar story in physics as well. Sorry. Should I allow? Deny? Please. Okay, thank you. Okay, so something disappears, but so here it was supposed to be, this is supposed to be 4D maximum n equal to 4 super Young mills, and this is supposed to be 3D n equal to 8 super Young mills. So even in this meeting, we have heard of this 4D n equal to 4 super Young mills several times, and we know they had fantastic properties like exact superconformal symmetry and S duality, and ADCF correspondence, of course, and some integrability. And it has been discussed in the literature very much. On the other hand, no one mentioned this 3D n equal to 8 in this meeting. And even in the literature, I don't find much. I don't find any result about this 3D n equal to 8 super Young mills. And this talk is about why that is the case. And I will show you, despite such a reason, we can still learn something interesting about this n equal to 8 super Young mills using the method I show you. Okay, so let me quickly remind you of the basic properties of this n equal to 8 super Young mills. Obviously, it is a world volume theory of D2 branes, which becomes M2 branes in the strong coupling limit. And as any other 3D gauge theories does, it becomes strongly coupled in the IR. And since it is strongly coupled, it is, as usual, it is difficult to do some standard perturbative analysis. So we may be interested in some protected observables like supersymmetric partition functions. However, in this case, even such an approach, examining the protected observables, is also tricky. It's not very useful since we have a different symmetry between the UV and IR. More specifically, we have a different UVI symmetry and IR symmetry. Indeed, there are better dual descriptions of the same fixed point, like ABJM and ADH and Quiver. In fact, they also suffer from the same issue. They have different UV symmetries and IR symmetry, as we know. So in the IR, we expect n equal to 8 superconformal symmetry, but in the UV, ABJM, for example, has just n equal to 6, and ADH and Quiver has n equal to 4, manifest n equal to 4. However, in those cases, we know how to map the symmetries. On the other hand, it is more tricky for this 3D n equal to 8. So as far as I know, it hasn't been discussed very much in the literature. More generally, sorry? SO7. No, is it?
Well, take a D2 plane by the way, the natural center is a super.
I see. Maybe I'm wrong. Yeah, so that's the correct. But anyway, so we don't know how to map this UV symmetry to the IR1. Yeah. Okay. And more generally, this 3D n equal to A super Young Mills belongs to a class of 3D gauge theories called bad, according to this Gaiotto-Witten classification. And bad theories include monopole operators, which decouple in the IR, whose naive conformal dimensions are less than 1/2, which violate the unitarity bound. Therefore, we somehow expect that there must be emergent symmetries which correct this non-superconformal R symmetry, such that the true conformal dimension of those decoupled monopoles should be 1/2 in the IR. The thing is that, okay, so when we try, if we try to compute some protected observables like supersymmetric partition function, we are only able to use the data from the weakly coupled regime, which is the UV data in this case. Okay, but if we use these data from the UV, it turns out naively the partition functions like a squashed sphere partition function or the index looks divergent. Okay, the question is, even though we have this divergent partition function, can we extract some meaningful information out of this? That's the question. And it turns out the answer is yes, if we use this mirror dualization algorithm. Okay, so here's the outline. So in the first part of the talk, I'm going to briefly review this mirror dualization algorithm. And I give you, and I explain the SQCD case as an example to demonstrate the difference between the good theories and bad theory from this mirror dualization algorithm perspective. And then I move on to the main topic, the circular quivers. And unlike this SQCD case, these circular quivers have two different types of badness, so which we call the local badness and the global badness. And for each case, I will explain their properties using an example. And at the end of the day, I will show you this 3D n equal to 8 as an example of this global bad theory. Yes, please.
Why APGM is not sufficient?
It is sufficient somehow. I mean, if you are just interested in n equal to A superconformal field theory, I think, yeah, it is sufficient. You can just use ABJM. That's true, I agree. But who knows? I mean, if we find something more about this n equal to A, because this somehow provides another dual frame, right? Although it is not very useful at first glance, maybe we can learn something. For example, if I try to relate, for example, the 4D n equal to 4 and 3D theory, if you reduce the 4D n equal to 4 theory directly to 3D, then what you get is 3D n equal to 8, right? And so if we understand, for example, the symmetry map between the ABJ and this n equal to 8, I guess it will be useful. We don't even know the symmetry map between this mirror symmetry. I guess what you mean by this mirror symmetry is the ADH and Quiver, right?
Just maybe giving like mirror dualization, you will do some mirrors.
Yeah, that's true. But in all the literature, people usually say, okay, we have a 3D n equal to 8, and its mirror dual is ADH and Quiver, because from the brain picture, you can engineer this n equal to 8 as just the D5 with a 1 and 5. And once you dualize it, we have this ADHM. On the other hand, if you imagine, if you realize this n equal to 8, just a bunch of D2 brains, then it is not clear how to relate this theory with ADH and Quiver. So indeed, in practice, we don't know how to map the symmetry between those two theories. Yeah, as you mentioned, we can work with ABJM, we can work with ADHM. There is another dual frame, which is supposed to describe the same theory, but we don't know how to relate so far. Okay, what is mirror dualization algorithm? So it is about 3D mirror symmetry, as Sean mentioned. So, which is typically an IR duality relating to 3D n equal to 4 theories whose Higgs and Coulomb branches are exchanged. And as we know, it has a very close connection to the SL2G symmetry of type 2B string theory, exchanging NS5 and D5. The mirror dualization algorithm I mentioned is an algorithmic and field theoretic framework for constructing the 3D mirror symmetry from two fundamental building blocks. Okay, let me show you. So these are the building blocks. So basically, the idea here is that instead of dualizing entire theory, let's dualize its field, which is either in bifundamental or fundamental field. Then we can cook up some more complicated theory just combining them. Okay, so that's the idea. Dualize the field rather than theory. Okay. Then what we found first is that this single bifundamental between two UN global symmetry groups is dual to rather complicated Quiver theory, looking like this. Okay. And you can recognize that. So this theory is nothing but just a one fundamental hyper sandwiched between the two TUN tails, okay? And we know that this TUN theory arises as a S-duality domain wall of this 4D maximal super Hwang mills. So I'd like to call this as a S-duality wall, okay? And then we know this TUN theory has a manifest U1 to the N topological symmetry, which should get enhanced to UN in the IR. And so on the right-hand side, we also have two UN symmetries, UN global symmetry, which are not manifest in the UV, but exist in the IR. They should be identified with the global symmetry on the left-hand side. Okay. So this is first duality, first building block. The thing is that when if I use this notation, if I use this Quiver, so if you recall the origin of this TUN theory, it is realized as a 3D domain world theory between the two forward maximal super Hwang mill related by S duality, right? So somehow, okay, so from the string theory perspective, this TUN corresponds to this S duality domain wall, which locally dualized this D5 into NS5 and vice versa. From the field theory perspective, it is also kind of machinery dualizing the fundamental field into the bifundamental and bifundamental into fundamental field under the S duality. Mm-hmm. From the field theory perspective, it is not. But you can see as a wall. Okay, so then let's forget about the name. Okay, we just have two blocks of TUN. Okay.
So why TS?
So we just couple additional U1. So usually we have a SUN flavor symmetry, right? We just couple another U1 global symmetry, which couple to the other part of theory by BF coupling. So when you gaze, you can actually couple it to the UN vector field, UN vector multiply rather than SUN vector multiply. Okay. Yeah, with the BF coupling. Yeah. Sorry, can you say again?
But technically, there's one man.
Oh, yeah. So one side is S duality. I'm not saying this entire thing is S duality wall. So this part is S duality wall. Yeah, so we have two tails. Yeah, there are parentheses, yes. Okay. But this is not very convenient because this enhanced UN symmetry is not manifest in the diagram. So I'd like to introduce this shorthand for the TUN with a dashed line where I represent this enhanced UN explicitly like this yellow square box. Okay, so you can regard this the block with a dashed line as a shorthand for TUN, where we represent both flavors manifest flavor symmetry and enhanced topological symmetry manifest. Okay.
You brings the refer to the wall as the version of cycle.
It's not really a five brane. So it's like a local S action of SL2Z along the space. Yeah. Yeah. Just interface theory.
Because the flavor symmetry is in SA and SN and what or real hydrogen.
Good question. Actually, I was a little bit sloppy. So probably the true symmetry should be UN times UN divided by U1 times U1. So this U1 is extra flavor symmetry on the top. And the emergent symmetry here should be, yeah, UN times UN. Yeah. Am I correct? Yeah.
What you said, all that, but not all. So the number of nodes is when -1.
2n minus 1.
So the rank should be 2n minus 1, which is S of UN.
Yeah, but so when I gaze this central node, so I just couple additional U1 vector with a pi coupling.
That's not good about the
Okay. Yeah. Okay. So this is the dualization of bifundamental field. And we can also dualize this fundamental field in a similar way. So this fundamental field, single fundamental field, is dual to the bifundamental field sandwiched between two TUN theories. Okay. Let me tell you more about the property of this TUN theory. So let's consider two TUN glued by gauging the flavor UN symmetry, which we call identity wall. So now we call these two TUN glued together as an identity wall. The reason will become clear shortly. So the moduli space of this theory is parameterized by BEV of the monopole operators, which are charged under the enhanced topological UN times UN symmetry. And once we compute the partition function, we can see that the partition function is proportional to delta of this x and y, where this x and y are the symmetry parameters of this topological symmetry. Therefore, we expect the moduli space should be smooth, where this UN times UN symmetry should be spontaneously broken to diagonal UN. Okay. And here I explain as I gaze the manifest the flavor symmetry here. But actually, you can also gaze the enhanced topological symmetry instead of this flavor symmetry. And in that case, we just have a swapped roles between the flavor and topological symmetry, but basically you have the same structure. So the moduli space is still smooth, and there is a spontaneous symmetry breaking. Okay. So far, I have introduced, yes, please. Not really. I haven't thought about that, but what the main message here is that it should be smooth. I mean, it shouldn't have any singularity there. Thank you. So we have two building blocks, and I introduce some properties of this S-duality wall or identity wall. But this is not the end of the story. So in practice, in order to apply this algorithm to the real theory, we need a small twist. Okay, so let me introduce a deformation of this S-duality wall. Okay, So as I mentioned, this S-duality wall or TUN theory has both the flavor symmetry or enhanced topological symmetry. So you can either by turning on the mass deformation or the monopole deformation to break one of the symmetry into the smaller group. Okay, so we can turn on the nilpotent mass terms or corresponding monopole deformation. And then the UN symmetry is broken to UM times U1, and I call this a deformed or asymmetric duality wall. Then what is the use of this? Using this deformed duality wall, I can dualize the bifundamental field between the two unequal ranks. In the previous slide, I showed the duality for the bifundamental between the same rank, but now you can generalize it to a bifundamental with the different ranks, like this, okay? And this deformed duality wall has another very important property, which is similar to Hwang-Witten transition in the brain cell. Yes, please.
How would you interpret each trimatic vertex on the dashed line?
How what?
How to interpret that? I mean, I would expect that, for example, a straight patch is the bifundamental.
So you mean this one?
Well,
Sorry.
either top, yeah, exactly.
Right.
The trigonometric section on the dashed line.
So basically you can, so let's assume you gauge the flavor symmetry, okay? Then these parts just look like 1 to n, originally like this. So this is the undeformed version. But once you just introduce the mass term, the important mass term, which break this un, okay? So it becomes something like m, and you have more flavors here.
So I am introducing also a Muslim.
Sorry. Yeah, that one. Yeah. So they originate from the link here. So when you break the symmetry, it becomes the extra flavors like this. Okay. So deformed S-duality wall satisfies a relation which is very similar to the Hwang-Witten transition of type 2B brain, which is basically essential thing when we realize this 3D mirror from the brain perspective, okay? But the thing is that this is purely field theoretic relation. So both sides, you can just interpret them as a theory. This is a kind of duality. But important part is that you can derive this relation as just a Higgs mechanism. So the important part is just a Higgs mechanism. Okay, so now we are ready to jump into an example. So let me show you an U2S scarcity with the 4 flavors as an example. Of course, the mirror of this theory is well known, but I will demonstrate how to derive this mirror from the purely field theoretic way using this mirror dualization algorithm. Okay, so let me first decompose this theory into the 3 pieces. 3 pieces. So of course, those 2 bifundamentals are trivial because one of the rank is just a 0. Oh, sorry. But I introduced them to incorporate this Fi parameter in a proper way. Okay, so we have 2 bifundamental and 4 fundamental field in the middle. So I apply the dualization relation I show you, the building blocks. So this bifundamental becomes this fundamental field sandwiched between the deformed S-duality wall. And this fundamental field, 4 fundamental field becomes 4 bifundamental field. Of course, there should be an identity wall in between, but they just collapse because, as I mentioned, their role is just to identify the symmetries, okay? And on the right-hand side, we also have the same structure, okay? Then you can recognize that this part is exactly what you observe in this relation, okay? So we can apply this Hwang-Witten move, field theory version of Hwang-Witten move.
The couple part comment after.
Yeah, so after dualizing each piece, I glue them back.
I get it.
Yeah. So I first ungauge, somehow ungauge, and then dualize and gauge them back. So I can apply the Hwang and Witten move on this side and this side as well to get this. And again, I have a similar structure, the same structure. So I can apply another step of Hwang and Witten move to obtain this. So at the end, what we get is just two pieces and two consecutive identity words in between. So as I mentioned, the role of these colliding identity walls are just identifying two symmetries. Or from field theory, in the field theory language, it's just Higgs. In this case, U2 times U2 into the U2, the diagonal U2. So in the end, what we get is just this Lagrangian theory, which is well-known mirror dual of the original theory. Okay. Of course, we can derive, we already know this from the brain picture, but here I just derive it using only field theoretic method, okay? Okay, so it is a field theoretic algorithm constructing 3D mirror. Yes, please.
Okay. So,
Mhm.
the class of good theories to which you can apply this algorithm. If I take a
Very good question.
I guess it not work. So what's the anyway?
Very good question. So I would say if you have some junction, like a star shape, it will be tricky. But unless you have such a thing, so you can apply to the linear quiver codes and circular quivers. Maybe somebody has some comment about other cases, but yeah. I think that's the humble answer, yeah. Yes, so as I emphasized, the core idea is that we should dualize each field rather than the entire theory. And since we can cook up some, as I just answered, we can cook up some more complicated theory than is just SQCD. So it can easily extend to linear or circular quiver gauge theories with some extra ingredient I will explain shortly. Okay. And more importantly, this also extends beyond the good theory. Okay. So let me quickly remind you of what bad theories are. So 3D n equal 4 gauge theories are to make chiral monopole operators whose spec parameterize the Coulomb branch of the vacuum modular space. And on Tuesday, I guess, Marcus already showed the generic formula for the R charge of the monopole configuration in 3D gauge theory. And if I apply that formula to the UN gauge theory with the fundamental hypers, I just get this relation, which only depends on the number of hypers and the rank of the gauge group. Okay. And as you can see, if this becomes equal to 1/2 or less than 1/2, the corresponding monopole should decouple from the theory due to this unitarity of the theory. And then this condition can be read like this. So if we have too small number of flavors compared to the rank, then the theory becomes bad, okay? Now, according to this Gaiotto and Witten's classification, if the conformal measure is exactly 1/2, we call it ugly. And if we have a conformity measure less than 1/2, we call it a bad theory. The thing is that in bad cases, if you try to compute the whatever supersymmetric partition function like a squashed sphere or index, the matrix integral, the original matrix integral, or the approximation for the partition function look not convergent. Okay, so naively they look at some divergent contribution. Okay. However, the thing is that if we apply this mirror dualization algorithm to the bad theory, it naturally reorganizes the partition function of a bad theory into the sum of those good theories multiplied by delta distributions. So in that sense, I would say the partition function of a bad theory is not really a function, but a distribution. Okay. Okay, let me show you a bad example. Okay, I increase the rank by 1, so we have U3 with 4 flavors. So again, I decompose it into the 3 pieces and dualize each piece using the building blocks. And then I can apply some steps of Hwang and Witten moves to get this theory. But unlike the previous case, previously we have just a colliding original identity walls. On the other hand, now we have a colliding deformed identity walls. Okay. Okay. So that caused the problem. Okay. So I can answer for the mirror dual of this bad theory in two steps. Okay. So firstly, so I would call this semi-Lagrangian dual as a mirror dual of bad theory. Okay. What I mean by this semi-Lagrangian theory. So it is a theory obtained by gauging the emergent symmetries of the Lagrangian piece. So if you look at this theory, so it consists of 2 parts. So each side, each part looks like this, and which can be written in the Lagrangian shape. Okay? But we want to gauge emergent symmetry of this Lagrangian, emergent topological symmetry of this Lagrangian theory. So strictly speaking, it is not fully Lagrangian, but somehow it can be constructed from the Lagrangian building blocks. So I would call it semi-Lagrangian dual. Okay, so this is the first dual description of a bad theory. But this is not the end of the story. We can further follow the arch flow from this theory into the deep IR. Okay, so let's look at this colliding identity walls. Okay, so you recall that if you have an identity wall, the role of its role is just to identify 2 symmetry groups, right? But now, so on both sides we have a U3 and U3 initially, but now we only gauge part of it. So we gauge U2 out of U3 on the left, and we also gauge another U2 in the U3 like this. Okay, so because now we don't preserve the full U3 symmetry, so there are 2 different ways of symmetry breaking. Okay, one is like this, and one is like this. So here, the red letters Z and W are the symmetry fugacities for the gauge fugacities, and the blue one, the Y, is the global symmetry fugacity. So we can identify Z and W and Y1 and Y2 in this way. It means we just break the U2 times U2 into the diagonal U2, and we just identify the global U1 to global U1. Okay. On the other hand, there is another way to identify the symmetry like this. So from physics point of view, this is nothing but just a U2 Higgs down to U1. So it means depending on where you sit on the moduli space, you have 2 different effective theory for bad theories. So one is this with a broken flavor symmetry, which is associated with this delta in the partition function. And another phase, which is described by this theory without any symmetry breaking, global symmetry breaking. Okay, so in the IR, this theory has 2 phases like this.
It's operation. It's just motivated by identities that the Summer has with the fish function. It's always good.
Yeah. Yeah. Yeah, so we have 2 phases. So pictorially, I would draw this relation in this way. So I have a bad theory, and we have its semi-Lagrangian dual, and it has a further flow into the deep IR, which can be described by 2 different phases, like this one, with a spontaneous symmetry breaking of the original U1 topological symmetry, and this one without any symmetry breaking. Okay. Good. And we are going to call them as magnetic dual frames. Okay. So to recap, bad theory has so not just this example. In general, a bad theory has a semi-Lagrangian mirror dual, which further arch flows to multiple magnetic dual frames in the deep IR. And the thing is that each magnetic frame is described by a good theory. So you can notice that both this and this theories are all good, okay? With partly spontaneously broken global symmetry, like this case, okay, which manifests as a delta in the partition function. So I should comment that in general, we expect the multiple magnetic frames with a delta associated, but sometimes or very often we encounter one single frame without delta, which means so we have a theory without symmetry breaking at some point on the moduli space, and the other places we have a effective theory with a spontaneous symmetry breaking of the topological symmetry. Okay. Since another comment, so since each magnetic theory is described by a good theory, you can also dualize this each magnetic theory to write down the theory on the electric side again. Okay. Then we call it electric dualization. Then I just so dualize this theory into this one, and this theory into this one. Okay. Then you can recognize that those frames associated with a delta is nothing are nothing but just a result of monopole Higgsing. Okay, so there are decoupled monopoles which should have a web, and this break the gauge group by certain ranks, and it becomes like this. So in general, if you start with the UNSQCD with the F flavors, then it has multiple magnetic or IR frames, which are given by U of R SQCD with F flavors, where this R runs from this to this. Okay. Okay. And this is consistent with Asser and Kramer-Nesset result, where you have the same nested structure of the bad theory in the IR. Good. Okay. So far I have described how we apply this mirror dualization algorithm to the bad theory. And any question?
And as to how the velocity there, which I guess means something that let along partition functions translates into the modular space. So suppose I want to look at the modular space of your original bad SQCD. How would you incorporate the fact that each of these cases move?
Very good question. So
That like a uniform section.
I'm not sure whether this is a precise statement, but basically it's a union. Okay, because the reason is that, so as you can see, those two theories are distinguished by the symmetry preserved. So in this case, the entire theory of the original theory is preserved, while here the topological symmetry is spontaneously broken, which is due to the web of monopoles. And this web of monopole describes the position on the moduli space. So, okay, then let's move on to the circular quivers. Yes, please. It depends on which level you are asking. So for any bad theories at the intermediate level, so let me go back to this diagram. So claim is that we have a semi-Lagrangian dual description of bad theory at the intermediate energy level. Of course, everything is IR duality, but you can also rewrite this semi-Lagrangian theory as a union of good theory in the deep IR. So in the deep IR, you can always write down the things in terms of good theories. Yeah. Okay, so now let's move on to the circular quiver. So if I consider circular quiver, the extra ingredient I need is just some extra symmetry, how to introduce those extra symmetries. For example, for circular quivers like this, we can introduce a baryonic symmetry under which this loop operator is charged. Okay? And from in our language, the way of introducing this baryonic symmetry is just the insertion of this shifted delta. So without B, if you just inserted this delta, it is trivial. But if you insert this shifted delta, then that it identifies the two variables in a shifted way. So you can introduce this baryonic symmetry. And as I mentioned, this delta can be realized as just identity walls with the shifted variables. But you can check this shift B on one side can be translated into the Fy parameter in the central node. Okay, and this is good because once we write things in this way, we can see that the mirror dual of this baryonic symmetry is nothing but just a topological symmetry. Because so if I dualize this by adding the extra S-duality wall on both sides, then both sides become just a trivial, and you're left with just a extra. So you cannot see it. So extra Fy parameter you introduce. Okay. So we have a mirror relation between the baryonic symmetry and the central diagonal topological symmetry. Okay. So using this, so let me apply this circular version of mirror dualization algorithm to an example. So let me first give you a good example, which is self-dual M2 brane theory. So let's consider this circular node, circular quiver with a constant length with one flavor at each gauge node, which is just a special case of this Cronheimer-Nakajima quiver. Okay. Then it is known that this theory is a low-energy effective theory of n M2 branes probing this C2 mod GL times C2 mod GL. And if you take L equal to 1, this is nothing but the ADHM quiver we saw before, which flows to the 3 n equal to 8 superconformability theory. Okay, now let's apply the algorithm. So we first decompose this quiver into the building blocks like this. And as I mentioned, we have to insert this shifted delta and the diagonal topological symmetry associated with this variable E. Okay. Then I can dualize each piece like this. So you can see that. So for example, this fundamental field with the XL velocity becomes this bifundamental field after the dualization, as I explained before. And also this bifundamental becomes this fundamental, okay, and so on. And similarly, so this baryonic symmetry and the diagonal topological symmetry becomes a dual topological symmetry and dual baryonic symmetry. And once I combine them together, I get another quiver gauge theory, which is exactly in the same shape, but now the symmetry fugacities are exchanged. So originally, I have X flavor fugacities and Y topological symmetry fugacities, but now Y appears as a flavor fugacities and X appears as a topological symmetry fugacity. So this is an example of self-mirror circular quiver gauge theories exchanging the identical Coulomb and Higgs branches. Okay. In this case, enhanced symmetry. Generally, I don't expect so for general L. Of course, when L equal to 1, we expect N equal to 8, but generally no. Is it correct? Anyway, so let's move on to the bad circular quivers, okay? So you can apply, of course, the same unitary bound works for the conformal dimension of the monopole operators of the circular quiver. So in this case, you have to check the effective number of flavors, which is given by this. And if this is smaller than 2n minus 1, the theory becomes bad, which we call local badness. On the other hand, there is another type of monopole operators in the circular quivers. So there are monopole operators charged under the diagonal UN, okay? Not locally, so not under the single gauge group, but it is charged under the whole chain of gauge group. And this leads to a new kind of badness of circular quivers, either globally ugly or globally bad. I will show you an example later. Okay, let me first explain the local badness of circular quiver. Of course, you can apply this mirror dualization algorithm to the local bad circular quiver, but in practice, it is more convenient to do this electric dualization directly, okay? So let me show you an example. So for example, if I start with this circular quiver, then you can recognize that this node, gauge node, is bad because it has 4 effective number of flavors, but the rank is 3. So we have too small number of flavors, okay? Then you can dualize this bad node into the smaller rank, as I mentioned, from f over 2, the integer part of f over 2 to f minus n. And in this specific example, we just have 2 cases. The first case is this one, which should be associated with some delta, okay? And the second frame is given by this. And once you dualize this bad node into 1, then actually another ugly node appears, which didn't exist in the original quiver. So we have an ugly node here. So we can also dualize this ugly node. Then we get just this one. So in the end, we have 2 good frames, which describe the IR dynamics of the original bad theory. Okay. So in this example, so to get a certain frame, there is only one order of dualization, okay? One way of dualization order. On the other hand, if you consider more generic quiver, maybe you have, to get a certain frame, there might be some set of equivalent ways of dualization, okay? So you can first dualize this node and that node and so on, or you can dualize this node first and other node and so on, and in the end you get the same frame. The question is the result independent of the order of dualization you take? Okay, so this is non-trivial. From physics perspective, we expect so, but this is not obvious at all, so we have to check. And we found that the answer is yes, of course, but given the conditions that the resulting frame should not break the axial symmetry belonging to this S over R symmetry of the theory. And the second condition is the resulting singlet after the dualization do not have vanishing conformal dimension when these delta conditions are imposed. The first condition is somehow natural because we expect n equal 4 dynamics in the IR, so it shouldn't be broken, okay? So this is okay. But second one is less obvious. And what we have checked, we don't have a proof, but what we have checked is that whenever we have this kind of situation, some frame with this condition, actually we can interpret, this is nothing but just some limit of other physical frames, okay? So we don't have a proof, honestly speaking, but we have checked many kinds of examples where if this happens, it is unphysical because it should belong to just a special limit of another physical frame. And under these conditions, we have checked whether the resulting frames are independent of the order of the dualization. We check millions of examples, and yes, it is independent. Okay, so this is about the local bad Quiver series. And next example is the global oblique Quiver theory. So I consider the circular quiver with a constant length and 1 flavor at a single node, okay? And this is known to describe the M2 branes probing C2 mod GL times C2. And obviously, this is, not obviously, but this is mirror dual to the ADHM quiver with the L flavors, which I will show in the next slide. And again, you can check that there is no, you can check that there is no gauge node, no local gauge node violating the goodness of local goodness of the quiver. However, there is a pair of diagonal monopole operators which are charged along the gauge groups of conformal dimension 1/2. So the theory is ugly. Okay, this diagonal monopole operator should decouple from the interacting factor. Okay, so yeah, let me apply this mirror dualization algorithm. So I first decompose this theory into these blocks and dualize each piece and combining them back. Okay, then as you can see, so this fundamental becomes bifundamental, and those bifundamental field becomes fundamental. If I collect them, I just get as I promised, ADH and Quiver with the L flavors. And on this side, the diagonal monopoles decouple, while on this side, they correspond to the trace part of adjoint hypers. So we have a precise map between the decoupled sector as well. Okay. Okay. So last example is the global circular quiver. So the global band circular quiver is given by this shape. So we have a circular quiver with a constant length, but without any flavors. Okay. And obviously, if we take L equal to 1, this theory becomes N equal to A super Young Mills. And again, there is no gauge node violating the local goodness. However, again, we find a set of diagonal monopole operators whose naive conformal dimension is 0. So they should decouple in the IR. Okay. Then what happens if we apply the mirror dualization algorithm to this theory? So for simplicity, let me first consider the L equal to 1 case, which is N equal to A super Young Mills. So we start with this N equal to A super Young Mills. If I decompose it, I just have one single bifundamental, right? So if I glue it, I just get an adjoint hyper. Then if I apply the mirror dualization algorithm on this, it becomes just a single fundamental with the two tails. But now I have to glue this tail together, right? So I get this semi-Lagrangian mirror, which looks like this. Okay. Okay. The non-trivial thing is that now we have to identify the gauge group with itself. Okay. So on one side, we have a gauge variables G1 to Gn, and the other side we also have the same set of gauge variables, which are now shifted due to this baryonic symmetry, topological symmetry of the original theory. Okay, so then we can classify the IR theories in terms of how we identify those two sets of variables. Okay, so specifically, if I consider N equal to 3 case, the rank 3 case, there are 3 ways of identifying the variables. One is the trivial one, and second one is like this, and third one is like this. Okay. So in this case, what you can see is that you identify G1 with a G1 plus 2 E, which is just the delta of E, and there are 3 of them. So we have 3 delta of E, and once you identify in this way, the theory just becomes 3 copies of QED with a single flavor. Okay, so you start with the U3 with a single flavor, but you just identify G1 with the G1, G2 with the G2, and so on. So it just decomposes into 3 copies of QED. The second way is a little more non-trivial. So we first identify G1 with a G1 plus 2, G1 plus E, which gives us the delta of E. On the other hand, if I identify G2 with a G3 plus E, and then G3 with a G2 plus E, then if you solve the equations, you can see that 2E should be 0, right? So we have delta of 2E. So here I just heuristically explain, but actually you can do more rigorous computation of the partition function. When you identify them, you get delta function, corresponding delta function. And then, so in this way, you should identify G2 and G3 together, right? So the resulting theory will look like this, where you don't have 3 copies of QED, you just have one QED with a single flavor and another QED with 2 flavors, okay, because you identify G2 and G3. Okay. In third way, we can do this, and the resulting theory will look like this. You want with the 3 flavors and 1 single delta of 3 times E. Okay, so this is the magnetic dual frames of this n equal to a super Young Mills. Why this is interesting? Everything is now Abelianized. Yes.
How about any constants that don't have conditions?
Yeah, exactly. So that's the important result. So the IR theory will be classified by partitions of n. Yeah.
Like, what do I ask this one? So if you look at the Quiver and also the last Quiver you have the reference set, so you don't say like the last Quiver gives you a singular, and you don't say it in the starting point. Exactly for all I'm listening.
So you're asking how to see this singularity from the magnetic dual frames.
I'm not expecting, now you will not expect to get something like a 3D with straight flavor just from everything.
Yeah, I mean, yeah, good question. Honestly speaking, I don't have a definite answer for that, but yeah, we should discuss later. Another question?
Just one question, what is the meaning at the level of H theory of these deltas, probably related to the...
So basically, this delta can be interpreted as a contribution of decoupled monopoles. So it depends on how you realize this. So if you consider squash the partition function, so you have this SB function, double sign function, and if you have a decoupled monopole, so you have a pair of the double sign, which becomes delta in this specific case.
So we say that the delta tells which heat and the Coulomb ratio.
Yeah, so that's an important point. So as you can see, actually we have 3 different kinds of delta. So delta of E, delta of 2 times E, and delta of 3 times E. And they are associated with these diagonal monopoles. So for super Yang-Mills case, forget about the remaining part. So the delta of E is associated with a monopole with a single flux. Delta of 2E is associated with a monopole with a 2 flux, okay, and so on. So I will tell you later, but this is somehow, so the effect of this is somehow not visible from the usual perturbative way. Okay, so I will address this point later.
The space of the H theory would be some pre-sector plus the model space of ABGM, 3 and 2.
That's a very good question. It should be, but I don't know how to see it from this picture. So basically, it means, so we should find a way to how to relate this partition function, partition function of n equal to a super Yang-Mills with that of ABJM, right? And it's at the level of symmetry, right?
But we have to have a full interpretation of the quivers associated. Like the delta, yeah, we need to give the things. But the quiver above, it's
But you should have you have 3 and 2, so you should have a symmetrized product of C4, and you are saying something similar. A2 singularity should be inside there.
We have a slope and it has 3 faces. They could be all together with one.
Yeah, I completely agree. In the end, we expect n equal to a superconformal field theory in the IR. But honestly speaking, I don't know how to read it from this decomposition of partition function. There should be a way, but yeah, I don't know.
Similar with the composition in cases that whether it's different. those levels.
You mean not super young mills, the circular quiver? Yes, we have a similar structure. I will show you later. Yeah. So again, so far I have discussed magnetic dual frames. And now we can, as I mentioned, we can also dualize each frame into the electric one by taking the good mirror dual. Okay. So in this case, so I can dualize each piece, 3 SQED, 2 SQED, single SQED with 3 flavor, using the known mirror symmetry like this. For example, for the last frame, we have this mirror dual theory, right? And as I mentioned, so this delta of 3E is also associated with a monopole with the 3 fluxes, and then it can it can be written as just a U1 theory with a Fy parameter multiplied by 3. Okay.
And you see those pictures, this picture here, those two pictures that you have, they look like a realization of the brain system. Right? You have 3 brains together, separate, or 2 and 1. Right?
Good point, but it's a little bit tricky. So it becomes clear when we go to the electric side, I think. Okay, so let's discuss it again on the electric side. So if I dualize all the frames into the translate into the electric side and interpret this delta as a diagonal U1 of this quiver, then what we get is 3 U1 or single U1 with another abelian quiver with a 2 node, or abelian quiver with 3 node like this. Okay, and this is different from usual symmetry breaking or Coulomb phase of the theory, because we know, so U engaged theory has this adjoint scalar which triggers this adjoint Higgs thing. And in that case, the generic cartons of sigma will break the U3 gauge group into the U1 to the third. And if some of them coincide, then the non-abelian symmetry will be restored. So somehow in the abelian, in the IR phase, you expect U1 to the third, or so U2 times U1 or U3, right?
Why do you disagree with what that's precisely what we do from the coincidental separate brains.
Maybe you are right, but my interpretation, my brain interpretation of this, the third diagram would be something like this, right? Because you have a U1 circular quivers. So if I have something like this, of course, this is just a Coulomb phase, right? But on the other hand, we have a circular quivers now. So somehow this is a cyclic configuration of brains, which identified again with the original point, right?
What are you doing?
So sorry. So this is NS5. This is NS5. So I just I realized that this n equal to a super Young mass in terms of D2 brains.
Okay.
So if I set up n D2 brains, this is just n equal to a super Young mass, right? And then in the Coulomb phase, for example, I can just separate. Oh, this brain, sorry. Yeah.
Here you go.
So this is, I don't have a flavor. So this is NS5, not T5. So I.
If you take E4 and you keep dualities, then you get 1 NS5 from 3. So, depending on how you do the T1, if you can, you get the extra NS5. But you could do it both ways. Okay, maybe we can discuss this later.
Okay.
So you can.
Yeah.
So you think that the D3 goes around the circle and ends somewhere else in the NS5, and then continues, but this would create more supersymmetry.
Indeed. So that's why I said it is difficult to interpret from brain picture. So, I mean, naively, so if I try to engineer this theory in terms of brains, I would do something like this, and it should go back to the original point such that we have a circular quivers. But
Is the
Yeah.
top to the bottom difference not more linked to these theories are not conformal? Like if you take U2 with an adjoint, it's not really a conformal field theory, but there is a point on its Coulomb branch or like on the moduli space where it does flow to a conformal field theory. But it's like more comparable to the 40 thing. And that's kind of why you see discrepancy.
I'm not sure I understand. So the first line is just our semi-classical intuition,
What
right?
people think, yeah.
Yeah.
But they're not conformal field theory.
Yeah.
Exactly. And I think that's the issue. That what you want to
Indeed,
study
indeed. I mean,
so you go to a specific point and then you do a local analysis of the conformal field theory. There you so
That's true. Yeah. So what I'm just saying is that it is hard to see this effective theory from the perturbative, usual perturbative way or some brain picture. But I completely agree. They are just a local theory. Yeah. Yeah, that's true. Yeah.
correctly.
Any other questions? Yes, please.
Do you see any suggestions for any of these?
No. Yeah.
Describing the same as a
So, good question. So I think this is also related to Sergio's previous question. How do we see the real structure of the moduli space from this picture? So in the most humble way, I would just say, okay, this is a computation of partition function, or some IR structure of the theory using which we can see using the duality relations.
I feel that component.
It should be.
Then you just take that.
Yeah, I agree, but I don't know how to see it. Yeah. Okay, so this is another example with a longer quiver. So I consider the U3 rank 3 gauge node with 4 gauge node, which can be decomposed into this way. Then if I glue them back, I get a similar semi-Lagrangian theory with more flavors. Okay. And then in the IR, they can be decomposed exactly in the same way, but with just a different number of flavors. And if I dualize each frame, then I get these electric frames. So one is just so this is usual Coulomb phase. This is similar to Coulomb phase. The U3 just is broken to the U1. On the other hand, so now we have a enlarged abelian quiver. Okay, so initially we have a length 4 abelian quiver, which now becomes length 8 or length 12. Okay. So yeah, so the BAV of monopole with a non-unit flux leads to new types of Higgs thing as a number of partitions of rank of each node. Good. And for general values of n and l, the partition function of a circular quiver with a constant rank we just saw can be decomposed in this way. So here, so this G1L is rank 1. I mean, each gauge node has just a rank 1, and that we have L gauge node. So circular quiver of L gauge node, and this is a circular quiver of 2L gauge node, and so on. And of course, the total length should be the same. So this number, so this coefficient and L1, L2, and so on should be classified by the partitions of the total rank n. Okay. Yeah, I don't know. Again, sorry, I have to admit, I don't know how to see the true relation to this superconformal fixed point. However, one immediate thing I can ask is, do we have the right number of degrees of freedom, for example, in the Larsen limit. Because if we expect this flows to the n equal to A, it should be dual to ADS 4 times S7. And we know that the degrees of freedom of the theory or free energy should scale like n to the 3 half, right? On the other hand, in this case, we completely lost the non-abelian nature of the gauge group. So at first glance, it is hard to imagine we have this n to the 3 half out of this, right? However, interestingly, so if I really count the number of degrees of freedom, then because we have this number of partitions, which scales like e to the n square root to n. So in the end, we recover this n to the 3 half in this way. So here, each frame doesn't show this n to the 3 half scale, but if you consider all of them, then you can recover this correct number of degrees of freedom. And obviously, this is different from how we get this n to the 3 half from the ADHM or ABJM. So in that case, for example, from the ADHM quiver, we get this n to the 3 half as a partial confinement or equivalent to partial deconfinement due to monopole condensation. Yeah, one node. Yeah. Yeah, it should be multiplied by L. Okay. So yeah, it exhibits the same number of degrees of freedom, but again, yeah, it is still unknown how to identify their partition function in a refined way. So that's the open question. Okay, let me summarize. How many times do I have? Okay. So thank you. 3D circular Quiver gauge theory has many interesting models, such as the low energy theory of M2 branes I show you. And a large class of these Quiver gauge theories, circular Quiver gauge theories are bad, not just local bad, they are global bad, okay? And our mirror dualization algorithm provides us a very systematic way of rewriting a partition function of this bad theory into that of the good theory with delta distributions multiplied, okay? And as I show you in the last slide, we have found a new pattern of monopole Higgsing, which can be read from this partition function computation. Yeah. I keep saying this, so it is still unclear the comparison between the n equal to A super Yang-Mills and other descriptions like ADHM or ABJM partition functions at the moment. Okay, I have a couple of slides more, but let me conclude here. Yeah.
I have a question on the thing.
Do you, in fact, it's a general feature of getting amplifying diagram people that overall monopole.
Yeah.
Zero, basically.
Yeah, yeah.
So,
we haven't explicit check, but we expect a similar thing happens. I don't think so, because it has a junction, right? I mean, the trivalent legs, right? This is new development. Yeah.
it's like addition.
No, I mean, you can, not. Yeah, because you have a dual, so whenever you have a dual,
Thank you. Yes, please.
Find similar with different kinds of symmetric groups like exo.
Very good question. According to Sarah's ongoing work, you can somehow apply this to USB group, but not SO group at the moment.
So SU.
SU, yeah, you can do it because we know how this topological symmetry appears in the partition function exactly. So you can just get SU and by gauging this topological symmetry.
I think
Thank you.